very much, and thanks to the organizing committee and the scientific committee for giving me the opportunity to talk at this beautiful location here. This is based on joint work with J.S. LeMay, Eli Vandenberg, and Marcello and Frankie. So just as an overview, tangent category is sort of a minimal categorical setting for abstracting ideas from differential geometry. And I say that as sort of in comparison to synthetic differential geometry, which is one of the original sort of categorical approaches to differential geometry. It's a very nice setting in which one can, synthetic differential geometry is a very nice setting in which one can make precise a lot of the sort of very old ideas about how to do differential calculus in terms of infinitesimals. It's a very nice sort of powerful setting. Tangent categories, by contrast, to show like what is the minimum things we can get away with to be able to do to abstract ideas from differential geometry from other settings. In sort of comparison, like as categories are to topuses, maybe tangent categories are to synthetic differential geometry. So a lot of recent work has been done to try and formulate various ideas for differential geometry in an arbitrary tangent category. So can you do things like talk about vector fields or differential forms or differential equations or vector bundles or connections? And so the proof that it's sort of like a good setting for differential geometries to show you all these things can be done in this setting. So what I'm going to talk about today is just a brief overview of what tangent categories are, and I'm going to talk about what connections are in a tangent category, and then I'm going to talk about what this gives when we apply it to tangent categories in algebraic geometry. So we've known for a while that there are tangent categories in algebraic geometry, like affine schemes and schemes, have the structure of a tangent category, but it wasn't clear what a lot of the general things you can do in any tangent category are when applied to those particular examples. That's what I started talking about today. So just a quick overview of what tangent categories are. The idea is to abstract sort of the essential features of the tangent bundle in tangent bundle construction in differential geometry. So for any smooth manifold, you can build this tangent bundle, which is a collection of all tangent vectors at all different points. So here we've got the sphere at a point P. You can write all the different tangent vectors at that point P, and you collect all those different tangent vectors at all the different points, put them together as a single thing. That's what we call a tangent bundle. It's not our smooth manifold. This is a functorial construction, so if I have a smooth map from n to n, then I can get another smooth map from tangent bundle of m to tangent bundle of n. So locally in coordinates, given a point and a tangent vector, what this is doing is applying the directional derivative. So you take the Jacobian of the map at that point P, apply it to the vector v, and that gives you a tangent vector in the Jacobian ring. And it's functorial in the sense that, it's preserved composition. That's essentially the chain rule. What's going on behind the scenes that makes this preserved composition is exactly a chain rule. So already we have some categorical structure for the tangent bundle. It's an endofunctor on the category of smooth manifolds. But that's sort of that's not very much structure. What else does the tangent bundle construction have? What other kind of categorical properties does it have? What other kind of structure does it have? This is the idea of a tangent category, first defined by Ierzitsky in 1984, and then myself and Robin sort of modified it a little bit and extended more in theory, I guess about 20 years ago. So the first bit to mention, you've got some category with an endofunctor on it, we'll call T, which we think of as a tangent bundle of some object. Now one natural translation you have is a projection map from the tangent bundle back down to the identity, so that's giving you picking out the point at which each tangent vector is associated. In general, we can't sort of assume that our categories might have all limits, because the category smooth manifolds, which we want to be an example, doesn't. So we have to ask certain limits to exist. So we have to ask that the pullback of n copies of the projection element itself exists. So you think of this as n different tangent vectors at that same point. So T sub nm is n different tangent vectors, an element of at some point scale with n different tangent vectors at that point. Now we should be able to add and have a zero tangent vector, and that's represented by natural transformations. First of all, plus from T to 2 to T. That's taking two tangent vectors at the same point, adding them to give a tangent vector at that same point, and then a zero section, so giving at each point a zero tangent vector. Now, this is half the structure, I'll get half in a second. What we're not going to ask is some kind of additional sort of scalar multiplication structure, some kind of vector space structure on each of the tangent spaces. Instead, what we get is interesting things related to powers of the tangent bundle. So you can take, because it's endofunctor, you can apply it twice, right? You get T squared. And it turns out that in smooth manifolds, there's a natural translation of T squared to T squared. It's not the identity. Or locally, it flips a couple of coordinates. And the interesting thing is, if you look at the naturality of that thing, the naturality is exactly symmetry of mixed partial derivatives. T squared f dy dx and T squared f dx dy. So you can sort of represent categorically a really important property of derivatives by a natural transformation from T squared to T squared. The other interesting bits of the structure, there's also a sort of lift thing that goes from the first order tangent bundle to the second order tangent bundle. So when you take a first order tangent thing and lift it up to a second order tangent thing. And this, we asked this how it's sort of universal property. And I'll come back to this one. It looks a bit odd, but it's sort of related to some stuff about connections. So it's saying that if I look at t squared, and I look at those things when I apply t of the projection, I get the zero vector. That exactly is the space of two first-order things in the base. And so it's saying that certain second-order things should be represented by first-order things. In addition to that, there's lots of various coordinates equations about L and C and plus and zero and all these things, which I'm not going to go into here. So that's the definition of a tangent category. Endofunctor was a bunch of additional natural transformations to satisfy various properties. So of course, the canonical example is finite dimensional smooth manifolds, the usual tangent bundle. There's also other examples. As soon as you go to like, if you want to do some infinite dimensional geometry, there's also tangent category structure there. So convenient manifolds are one example. They have a category structure of a tangent category. If you heard about Cartesian differential categories, that's a category, some kind of differentiation operation. Those are tangent categories as well. Again, synthetic differential geometry, if you focus on the microlinear objects, that's a tangent category. I mentioned here category of affine schemes and schemes. We'll come back to that in a little bit, talk about what the tangent structure there is, what the tangent bundle of an affine scheme or scheme is. And there's also other examples. There's also, interestingly, many ways of constructing tangent categories from existing ones. So, for example, as long as you have enough sort of limits that behave nicely, the slice of a tangent category is again a tangent category. All sorts of constructions like talk about tangent categories of vector fields of an existing tangent category, or tangent categories of objects of connection to tangent categories. So it's sort of been surprising to me how many new tangent categories have been constructed of existing ones and how many models there are. There's also extensions of this theory to infinity categories, which Michael Ching is going to talk about later, sort of related to Googly's functor calculus. Okay, so we're going to talk about what a connection is going to look like in this setting. So I want to talk about the most, since this is the most general setup for a connection. One thing that's difficult about connections is lots of different definitions of them, lots of different settings, and they each sort of express different properties. And I've sort of found it hard to parse all the different, how those things are related. Part of this work is trying to understand how these different definitions are related. But I think one of the ones that I find easiest to sort of grasp a little bit is the one that Ehrlichman did, sort of when you've got some kind of bundle, what a connection it is. And so it's a way, I think, of relating tangent bundlers. So you've got some kind of map, E over M, got some big space E, some space M, and a projection from E down to M. And it's going to be a way of sort of relating the tangent vectors of E to the tangent vectors of M. Now you always have, of course, T of Q, this is functorial, that transfers tangent vectors upstairs. We've got a point here, some tangent vector up here. So it gets transferred down to a tangent vector down there. So I can always do that for any map from E to M, obviously. But one thing else you have, in addition to that, is you have sort of special vertical vectors upstairs. If you look at tangent vector upstairs, you transfer to something downstairs. Now, obviously the zero tangent vector is going to get transferred to the zero tangent vector here. That follows from one of coherence acting for a tangent category. But there could be other things here, that follows from W, which when we apply T of Q of it, could end up being the zero tangent vector downstairs. So we'll call those things, in this differential geometry notation, the vertical vectors. So vertical vectors. This relative is Q, of course. T of Q of W equals 0. And so one perspective on a connection is that it's a way for every tangent vector upstairs to get associated to a vertical thing. And that's related to what people call a connection term. So one perspective on connections is that it's given anything up here, there's a way to sort of project it onto the vertical subspace there. That's one perspective on them. Another perspective is that there are also ways of lifting up tangent vectors downstairs to tangent vectors upstairs. So we've got some kind of thing that's called A down here. Maybe I might be interested in having some way of transferring the tangent vectors downstairs to some kind of tangent vector upstairs, called each of A. And it turns out that that's also related to one way that people talk about connections. It's a way of transferring the tangent vectors downstairs to the tangent vector upstairs. Now it turns out in the full generalized tangent category, you sort of need both parts of it. In like differential geometry and smooth manifolds, the sort of vertical retraction thing and the horizontal lifting thing, either of them determine the other. But in a general tangent category, you sort of need all the structures. So let me go through what this will look like then. I guess before I get into that, so I need also a couple, be able to take certain pullbacks with this map from E to M. So we sort of talk a little bit trying to find the best way of talking about which maps preserved by which powers of T. So I think this is sort of a good definition that A t-display map is something for which the pullback of any map along t to the power n exists and is preserved by h t to the m. So every pullback along f and t of f and t squared f exists, and all those pullbacks are preserved by h t to the m. Now again, smooth manifolds, not all maps will have this property, but submersions do. So submersions are going to be these examples of t-display maps. If you go to a study like synthetic differential geometry where the tangent bundle functor is representable, then all maps are t-display maps, so you don't have to worry about this condition. So what do we need to talk about connections? First of all, we're going to need to talk about this space of vertical vectors, right? So this vertical bundle, it's going to be this pullback, right? The thing for which t of q goes to 0. So those would be the space of vertical vectors. We also want a space where we can talk about having a tangent vector downstairs and a point upstairs. That's going to be this pullback here. The pullback of the tangent bundle along E. Point up here then is going to be a point upstairs and a tangent vector on the base downstairs. Okay. So then when we've got this kind of t-display map, kind of abstract bundle, we've got sort of the inclusion of the vertical vectors into all the tangent vectors upstairs. We've got this kind of descent thing going from the tangent bundle down to the horizontal bundle, which, again, one component sort of moving this thing downstairs. The other thing keeps track of the original point we're on. As a connection, you want things going backwards, right? So you want to have this vertical projection and this horizontal lift. Again, in smooth manifolds, you can get away with one or the other, but in general, you need both. So it's going to be structure, it's going to have an R as H, and satisfying a bunch of axioms. The first one is, I was mentioning, is sort of R is going to be retracted by inclusion, H is going to be a section of another thing, and then there's various axioms to sort of keep things nice. One orthogonality, too, if you sort of lift up with the horizontal vector, that should be, it should have no vertical component. So this is, in Cutting-Harris manifolds, exactly represents Aristotle's notion of a connection on a fiber bundle. Actually, his definition worked on any submersion, but since then everybody sort of talks about connecting on fiber bundles, but you don't really need the extra substance of a fiber bundle. It turns out that just any submersion is fine. So that's what a general connection is going to look like. But I'm going to mainly focus on one particular kind of bundle you could have in a tangent category. And I think these are quite important, and you'll see why. What we call differential bundles. This is definition of Robin and I 7 years ago. So a differential bundle is going to be a t-display map, so it has all these pullbacks. But additionally, it has an additional lift map from E to T of E, and this diagram here is a pullback, which looks similar to the pullback diagram in the tangent categories. That's exactly expressing what the vertical vectors look like. So in general, again, the space of vertical vectors, who knows what it looks like for an arbitrary EQ to M, or QE to M. But in a differential bundle, you ask that this be particularly trivial, right? It just be the product of two copies of E. So in other words, if I have a vertical vector like this in here, well, it has some base point E, but in addition I can represent it by some other point of E. So every sort of tangent vector here that's vertical is actually just really a pair of elements of E. So making, saying the vertical bundle is very simple in some way. So the vertical bundle with differential bundle is trivial, and by the early definition, each tangent bundle is a differential bundle. Now this kind of property had been looked at in differential geometry, but not sort of isolated as its own thing. And what's interesting about it is, what does this give you? What are the differential bundles in the category of smooth manifolds? They turn out to be exactly smooth vector bundles, which I find interesting because smooth vector bundles have a local triviality condition, and there's no kind of assumption of local triviality here. There's just an assumption of what the vertical bundle looks like on this lift map. But it turns out that smooth manifold differential bundles are exactly smooth vector bundles. So Robin and I sort of knew that smooth vector bundles were differential bundles, but Ben McAdam a few years ago showed that actually all differential bundles are smooth vector bundles. So in this category of smooth manifolds, then a connection on a differential bundle, now a connection on a vector bundle, is the same thing as the standard notion of a causal connection on a vector bundle. Okay, so I want to move to a bit of algebraic geometry. So, talk about category of affine schemes. So, you pick some ring R. The category of affine schemes, typically defined in a very complicated way, they're tended to be equivalent to the opposite of the category of R algebras. And so we can just think of affine schemes of R as the opposite of the category of R algebras. This turns out to be a tangent category. And what's the tangent bundle of some object A, some algebra A? It's the symmetric algebra of the Taylor differentials over R of A. Now, if you haven't seen either of those things, you can look at what is this nonsense thing, but it turns out to be very straightforward in most examples you're interested in. So the way you sort of think about varieties in this category of affine schemes, if I'm interested in, say, the variety y squared equals x squared plus x cubed, solutions in R look like this, then the associated algebra, we work with that in category of affine schemes. Category is a polynomial integrating two variables, quotiented out by this relation. And what is then the tangent bundle, the symmetric algebra of Taylor differentials? Well, it's actually quite straightforward. So you just take the polynomial ordering as sort of a D generator for each of your existing generators. So for x and y, you have dx and dy. You keep the existing relation, and you add in a derivative of that relation as well. So you just d this thing here. So you get 2y dy minus 2x dx minus 3x squared dx. So to calculate the tangent bundle, we use first year calculus to do this, right? Just present them with some polynomial equations and differentiate those. So that those as generators for ideal, quotient out by that, and that's what the tangent bundle is supposed to be. Now, is this, like, in what sense is this actually a tangent bundle? Well, you can actually calculate some of the tangent spaces to see if this is actually the right thing. So, in general, if I want to know what the tangent space is at a particular point, that's going to be the pullback on some point of the tangent bundle at that point. In the category of R algebra is opposite. R is a terminal object. You represent a point by sort of thing which evaluates the polynomial at that point. If you calculate this pullback, you calculate algebra R, say at this point negative 1, 0, which is here, you actually get, after you calculate this, that it's just isomorphic to the polynomial in one variable. Sort of dy is free, dx is entirely determined, which is exactly what we want, right? Because look at this point here, the tangent vector should be completely free to y and not free to x at all. So that's giving a sense that it's sort of doing the right thing. Now, interestingly, you've got this point here, right? This sort of singularity. And you calculate the tangent space there too, and it's two-dimensional. So it doesn't know what to do whether you're going x to y direction, so it's completely free there. And so what I think, one thing that's interesting about this example is that it shows tangent categories can involve examples where you've got weird singularities, right? Your tangent space is different dimensions at different points, which is kind of cool. So then the question is, what are all these things I talked about earlier in this particular example, say, of affine schemes? So what are the differential bundles? What are connections? What are connections with more general T plane maps? And what happens if we generalize from affine schemes to schemes? Okay, so this is something which I didn't know for a long time. So we worked on and thought about differential bundles and connections quite a while ago. I sort of, know that there's 10 categories of affine schemes and schemes. Like, I have no idea what these concepts give you in these particular examples. I thought it must be something wacky, something really weird in algebraic geometry. Algebraic geometry is complicated, there's something, some weird kind of thing which you get out of this. It turns out to be very straightforward. In 10 category of affine schemes, differential bundles are exactly opposite of category modules over R. Which really surprised me because it's like, this sort of condition about the vertical bundle, which doesn't seem to have anything to do with, maybe give the right sort of notions with manifolds, and here it's also giving sort of the right notion of the right kinds of things in algebraic geometry, of course, by the modules opposite. Just a rough idea of how this works. So given an R module, again, a symmetric algebra is a construction from a module is going to give you a differential bundle. And if you're stuck with a differential bundle, you can show that you can extract a module from that, and the original thing is isomorphic to a symmetric algebra with that. So it's showing that, differential bundles in the one category of smooth manifolds are smooth vector bundles, which is great. In the other category of affine schemes, getting modules. So I think it's pretty cool. I don't know of any sort of general characterization which in one case picks up module, in the other case picks up smooth vector bundles. There's obviously relations between these things, but sort of a general definition which in one case gives you this, in another case gives you this. I don't think I've seen something like that before. So it's showing that differential bundles are kind of core in some way. Again, Michael Ching is going to talk about differential bundles in the infinity tangent category set. Yeah. Well, so then what does connections give us? And fortunately there is an existing notion of connection on a module due to Causul way back in the day. It's some kind of R linear map from a module to the Taylor differential of A, and it's over M, satisfying some kind of Leibniz condition. This may be a definition of connection you've seen before. And so what JS and Eli still did was show that indeed this matches up with the notion of tangent category notion of connection we talked about earlier. Even though again it looks nothing like this sort of nothing initially looks like a sort of vertical retraction or horizontal lifting thing here, it does turn out to be the same thing. roughly, how does that work? If I've got a module, which is a differential bundle, which is a symmetric algebra of some module, then a connection is going to be this lifting thing from a tangent bundle, tangent vector in space, with a point out here. But that's the opposite category of our algebras, so flipping everything around, it's mapped in this direction here. Then it turns out that all the axes I talked about earlier sort of tell you that really the interesting action is sort of happening with the M. This sort of symmetric stuff sort of goes away. There's the killer differentials here, and then here as well. And you get the satisfies Leibniz rule as well. So it turns out that this kind of geometric notion, when you apply it to this particular case, gives you the pre-existing notion of connection that people have come up with before. There's also notions of curvature of these things. That's really one important thing about a connection to determine some kind of way of talking about how the spaces or some kind of bundle is curved. And it turns out these definitions, we have one for tangent categories, general setting there, and there's one for definition of curvature for these kind of module connections here. They correspond to almost exactly just up to a factor of 2. So, if your ring has characteristic 2, then they're not going to be the same, but if your ring doesn't have characteristic 2, then they're basically the same thing. That's cool too. Everything pretty much goes through for schemes as well. Schemes are just sort of glued together affine schemes. So the category of schemes, the differential bundles are now quasi-coherent sheets of modules as opposed to just modules. There's a notion for connection to those things, and those things correspond as well. So everything sort of goes through nicely for schemes, mainly just because everything's sort of affine locally defined. Lastly, so I talked initially about sort of very general connections, right? I focused on the particular case when the bundle was a differential bundle, or the vertical bundle sort of has this triviality to it. So what does that look like, again, to category affine schemes or schemes? When I mentioned the abstract, I thought this was kind of a new notion. I couldn't find anything which this sort of corresponded to, but it turns out there is a notion of connection to Grothendieck, which I initially thought was just a sort of version for modules, but expressed in a different way. But it can be applied to the more general case. And after looking at it a bit with Marcello and Geoff Boyce, it kind of looks like they are very similar. You can do some more work to show that they are in fact the same, but I'm reasonably confident they're very closely related as well. So Grothendieck's notion of general connection should be what we get from this general notion over here. But more work to do on that. Okay, so just to sum up, you look at tangent categories of affine schemes and schemes. Differential bundle and connection give you module and connection on module. And then if we think about the more general connections, it seems like it's related to Grothendieck's notion of connection, which is related to an infinitesimal thickening of the diagonal, but more work needed to do that. Other than that, here's references to all the things. All the results I'm talking about are in an archive paper, which is put on the archive yesterday. All right, thanks very much, everyone.
So I have a question, actually. If you went to an algebraic geometer and showed them your definition of differential bundle and the theorem of U and JS, would they say, oh yeah, or would they be shocked, or what?
I don't know. When we submitted it to one place, one referee said, oh, this is probably an EJ or SGA, but I couldn't find it. So
in the 5,000
yeah, that's what it is. I don't know, I think it's new. But I guess talk more algebraic geometers, but I get the sense it's not like, oh, I guess that's okay. So, I don't know.
Okay. Other questions? Yes?
Yeah, thanks for the talk. It was pretty interesting. I had a lot of questions I feel out there, but when you talk about connections and these differential, you normally also have like a Lie algebra you can associate to it, and this curvature perhaps gives you curvature, but you think there's enough data in these tangent categories to start constructing.
So is the question like if you need Lie algebra stuff to do all of the connection things, or
no, it's
is there Lie algebra stuff?
Is there Lie algebra you can associate to?
Yeah, so I'm not sure with Lie algebra is related to connections. I have to look at that more. We do have, that the vector fields in a tangent category have a Jacobi identity, so they form a Lie thing. That's sort of an external object. It's not an internal object in the category.
No, I expect something external.
Yeah, no. So the vector fields form a Lie algebra, but I don't know related to connections. I have to look at that more.
Okay, yes.
Back there?
Sorry.
No, you go ahead. I think you had your hand up first.
Okay, sure. A I was wondering if you had some sort of a junction by which you could generate tangent structure on a wider class of categories, and whether some like less geometric categories like top or something would then be equipped with more geometric structure. So by doing this.
I think, I haven't looked at that too much myself, it's a good question. Robin at some point was looking at free tangent categories, I don't know where he is, but I'm sorry for that. But no, I don't know much myself about trying to try that kind of thing. Yeah. Good question.
Yep, go ahead. Yes.
This is more a suggestion than a question. I think that Grothendieck connections are your connections in the smooth case. And then the general, I mean, the problem is when the scheme is not smooth, the high differential information is not encoded in the tangent bundle. So perhaps there's a
it could be, yeah.
high connection in the abstract sense that takes care of singularities.
Yeah, and I have an idea of what higher connections would look like, because it's like the connections are like a splitting of the TE into components. The higher connections would be splitting of the higher tangent bundle things too, but the assumption of smoothness, that's a good point. I mean, as soon as things are not smooth, then like connections don't exist anymore too. So that might be like already you need smoothness just to have connections to exist at that point. So, but it's a good point to think about smoothness. Yeah.
Richard.
So among the kind of quasi-coherent G or whatnot, you've got the invertible one, so the line bundle.
Yeah.
So did you think about whether you can characterize abstractly things that correspond to the line bundle?
That's a good question. No, I haven't thought about that. Those are certainly important. Yeah, important classes of things. I have to look at it. I don't know. It's a good question. It's really good down. It's a good question. Yeah. I haven't thought about it.
We good?
There's nothing bad.
Sorry. Yes.
I just want to see this slide of where you mentioned about the quasi-coherent sheets.
The key one? Yeah.
Yeah. So I thought the differential bundles for the affine schemes are the modules.
Yeah.
And the quasi-coherent sheets, it is, I mean, maybe I'm doing something wrong, but the differential bundles here, are you saying that these are the quasi-coherent? Okay, this is just affine schemes.
This is now on schemes. It's supposed to.
Affine schemes.
Yeah, now on schemes. Yeah.
Yeah, so for general schemes, it could be like for each affine piece, it's like this.
Yeah. For each affine piece looks like modules. Yeah.
Okay, I think we better move on to the next talk. I'm sure Geoff will be around over lunch to chat about this stuff some more. So let's thank our speaker again.